with his famous book, To Touch the Face of God. And he's currently working on America's Big Bang, a social and cultural history of the origins of the universe. And that is the topic of his next book. So I'm very pleased to introduce him now to speak about order, scale, and origins, concepts of the universe from Copernicus to the cosmic microwave background of radiation.
Thank you. It's sort of, I think, quite appropriate for a study day on the Big Bang that I'm, as it were, packing quite a lot in to this particular talk, and I apologise if I seem to sort of go a little bit kind of quickly over some fairly major developments, but hopefully you'll forgive me, and I'll see if we can perhaps investigate or explore some of these in a little bit more detail as I go along. So, in the year 1500, Europe knew less than Archimedes, who died in the year 212 BC. That was the view of the English philosopher Alfred North Whitehead in his magisterial 1925 volume Science and the Modern World. Now, historians are no longer quite as comfortable as they used to be with the idea of using the term the Dark Ages as a synonym for the medieval period. Historians have more recently kind of itemised the many kind of artistic and cultural achievements of the medieval period in Europe, and disprove some of those sort of standard cliches about medieval understandings of the physical world. You know, the idea that if you kind of walk far enough in one direction, you're eventually going to kind of tumble off the edge of the earth. Those are now pretty firmly discredited. But with respect to astronomical knowledge, Whitehead's estimation still seems to hold pretty fair. From the accounts that survive, we know that the ancient Greek world, the world of Archimedes, was host to some striking advances in astronomical observation and theory. Some writers and thinkers, at least, were aware that the Earth rotated, and there were some attempts to account for the movement, the motion of the planets. The fact that if you sort of are looking at them in the sky, they don't just, as it were, move in a kind of consistent path. They actually, there's a kind of retrogression. They move that way, and they go like that. And also some attempt to account for the fact that sometimes they look closer, and sometimes they look further away. And at least one Greek astronomer, Aristarchus of Samos, whose work was described by Archimedes, he argued that the Earth moved around the Sun. So you at least get a kind of at least one instance of a kind of heliocentric rather than geocentric interpretation. But these sort of ideas, these quite diverse ideas, were they generally kind of ran quite contrary to other, probably more compelling themes in Greek culture and thought. So Platonic philosophers, very keen on this kind of geometrical, the kind of geometrical perfection of the sphere, and also on the idea that there's a kind of around the sphere or around the kind of circle. Associated with the circle is this idea of kind of uniformity of motion, where everything proceeds at the same speed. And they took that as that kind of, as it were, philosophical principle of geometrical perfection as their model for the cosmos. Also, classical Greece was a pretty kind of rigid elite society that tended to associate hierarchy with virtue, and to associate change, as it were, the danger of civilizational collapse. And therefore, we can see, as it were, the kind of preference for the kind of cosmology that we associate with Aristotle, Plato's intellectual heir. And that is a kind of cosmos that was essentially immutable in its large-scale structure that didn't really change, comprised of perfect spheres, and with the upper boundary marking the kind of realm of the divine, as it were, the higher up you go, that's where the sort of sphere of divinity, as it were, and with sort of going down then through the kind of fixed firmament of stars, down through the regular circular orbits of the planets, right down to get to the corrupt, profane body of the Earth at its centre. Now, there were some attempts by Greek astronomers, Claudius Ptolemy most notably, to kind of reconcile the basic principles of Aristotle's cosmos, this kind of geocentrism and its kind of fetishization of the circle, with what you could actually observe about the planets in terms of their motions. And so Ptolemy explained the retrogression of the planets and their kind of periodic proximities, that they kind of move closer and then further away, by incorporating epicycles. That was sort of Ptolemy's attempt to as it were, reconcile this cosmos with what could actually be observed in terms of what the planets actually did, and epicycles obviously still preserving that idea of a circle. Unfortunately, Ptolemy's refinements, along with many other classical scientific texts, tended to disappear with the end of the Roman Empire, only to be rediscovered many centuries later when a translation of his work was made from a surviving Arabic text. Until then, and even to some extent thereafter, Aristotle's, as it were, simpler model held sway. And it held sway largely because it's kind of association of height with divinity, depth with corruption, mapped very neatly on to the Augustinian theology of the medieval church. Moreover, given that theology, the kind of theology of the medieval church, tended to insist that man's only hope of salvation lay in devoting his attention to his relations with God, there were relatively little cultural stimulus towards the sort of study of the cosmos that might have drawn attention to the inadequacies of this model. St. Augustine himself declared that he didn't care to know the courses of the stars. So the problem is not, as it were, direct church censorship. It's a kind of intellectual hegemony. Though you do get the kind of rediscovery of Aristotle's writings on the natural world in the 12th century, and that helped to encourage the kind of rebirth of natural philosophy. For example, you can see this in the writings of St. Thomas Aquinas. They also, that kind of rediscovery of kind of Aristotle's writings also reinforced the authority of his overall cosmological scheme, albeit that it was now spotted here and there with Ptolemy's annotations. So those who observed the skies, those who bothered to observe the skies, basically expected to see what Aristotle said they would see, and if they saw something different, it was not Aristotle, it was as it were their eyes. Now, Aristotle's cosmos was eventually dismantled by the Copernican revolution, but that dismantling, as Arthur Koestler observed in his seminal synthesis, probably, to me, it's one of the best written books on cosmology. Not necessarily makes it the best book on cosmology. Does get a few things wrong, but Koestler argued that this kind of dismantling of Aristotle's cosmos by the Copernican revolution was accomplished along a kind of crooked path, a lengthy crooked path, and it only really attained completion with the establishment of a kind of coherent alternative cosmology in the form of the Newtonian system. Nicholas Copernicus himself was a very timid revolutionary. He really, as it were, just as equally deserves the term the last proponent of Aristotle's cosmos as he does the kind of father of modern cosmology. His principal theoretical innovation, which is the claim that the sun and not the earth lay at the center of the cosmos, wasn't informed by Copernicus going out with looking at the movement of the planets with his own eyes. He did very little of that. He didn't have a kind of an extensive program of personal observation. He was basically dependent on the observational data that had been produced by classical astronomers. What he wanted, what he was arguing from then, was the desire for a cosmic system that was more perfect even than that produced by Aristotle. That is one that did without the kind of epicycles of Ptolemy, and that produced planets moving in kind of perfect, uniform motion, perfect circles in uniform motion, at a kind of uniform velocity. But the only way he could achieve that perfect model was to displace the Earth. And so, as it were, the displacement of the Earth is the consequence of that kind of almost sort of philosophical desire. Unfortunately, he ended up rather disappointed by the cosmos that he produced, because we now know that the planets don't move in perfect circular orbits according to a uniform velocity, and so therefore this kind of Copernican model could only work if he, just like Ptolemy, incorporated epicycles as well. So he was aware of some of the kind of weaknesses of his system. He was also very fearful of mockery from quite a powerful establishment of natural philosophers who still subscribe to kind of Aristotle's model. And so Copernicus was very kind of hesitant to publish a detailed account of his system, and eventually it kind of had to be kind of wrestled out of his own hands by others who sort of walked it to the printers and put it into press. And the book that resulted on the revolution of the celestial spheres was a famously tedious read. Koestler called it the book that nobody read, which is a slightly exaggerated claim, because recently it's been revealed you can find lots of kind of fairly well annotated copies of the first and second edition all around Europe. But it's certainly true that the Copernican revolution needed more than the publication of Copernicus' own theory to overthrow Aristotle. It needed, for example, the work of Johannes Kepler, who, making use of more recent observations, replaced Copernicus' epicycles and Copernicus' insistence upon uniform velocity with elliptical orbits. So these kind of egg-shaped orbits, in which the planets moved more quickly as they approached closer to the Sun, and then more slowly, as it were, away again. That was, as it were, observationally much more kind of accurate in terms of the description of planetary motion. And it also took Galileo to make Copernicanism a kind of a core celebre. He used the telescope to show that the phases of Venus, as it were, what you could see of Venus in terms of whether it had a kind of full phase or whether it was present shape, were completely consistent with the model of the kind of geocentric. The idea that kind of Venus was actually going around in motion around the Sun. And he also basically kind of was a provocateur, provoked what we can actually argue is a hitherto relatively open-minded Catholic Church to ban both Copernicus' volume and his own defense of heliocentrism in his book Dialogue on the Great World Systems. What made this event get banned, of course, this is the year of the Reformation, so there's an awful lot of people in Protestant Europe who think who are quite attracted to this scandalous text, and therefore gets a lot of kind of prominence and gets published there too, and so that helps to publicise Copernicus' ideas. The Copernican revolution, of course, was principally concerned with the structure of what we now name the solar system, which is at that point limited to the Sun, to the 6 planets that have been identified at this point, and Earth's own moon, supplemented by the 4 moons of Jupiter that Galileo discovered with his telescope. What lay beyond that system was not really the subject of lengthy analysis by any of the main actors in the Copernican revolution. Kepler seemed to assume that the kind of canopy of stars, firmament of stars, was indeed fixed in space, which is the kind of, it's quite interesting that you see that sort of similar view coming out in some of the texts that Helen was looking at. Fixed in space at an immense distance from the sun across what was essentially empty space. So there's a kind of solar system, then you have to go an enormous long way until you get to that kind of fixed canopy of stars. That tended to be the view of Copernicus. Kepler. Galileo, looking through his telescope, had noted that you could see some stars with his telescope you couldn't see with the naked eye, which suggested that some stars were actually more distant than the others. But he didn't tend to reflect very expansively on the implications of that. Moreover, there wasn't really anything in the Copernican revolution that directly challenged the biblical narrative of creation, or indeed the kind of standard estimates of the age of the universe, which were basically at this point calculated on the basis of adding up the consecutive ages of various biblical figures until you came up with, as it were, an overall age for since the time going back to Adam. Kepler himself pinned down creation as having occurred in 3992 BC. But the Copernican revolution, having shattered Aristotle's cosmos, did open up the intellectual space for further innovations. By discarding the concept of an immobile Earth, Copernicanism had also effectively removed a reason for all the stars to kind of rotate around it, you know, as if they were kind of clinging to the inner surface of the sphere. So it kind of did open up a much larger, deeper universe for exploration, just as it were, telescopes were beginning to move beyond their first generation designs. Also, in addition, having drawn a distinction between the sun as the kind of stable core of the system and the planets which were orbiting around it, Copernicus established, the Copernicanism kind of established the ground for subsequently identifying the sun as a star in a much wider universe of stars. So as it were, like all the other sort of bright objects that you could see in the sky, and therefore open up the possibility of conceiving of space as essentially a kind of homogeneous whole with no special regions that were, as it were, so a homogeneous whole that was subject to universal laws. So all these sort of things that were the potential for all of this was created by the Copernicus, by the Copernican revolution. And it was Isaac Newton who brought coherence to this new cosmos, and who, in doing so, folded its properties into natural laws which were applicable to the universe as a whole. So Newton's theory of gravitation explained what Kepler had discovered, that is, the changing velocities of the planets as they neared and then moved away from the sun. More generally, it established the kind of principle of a mutual attraction of mass that kept the moon in its orbit around the Earth, and the Earth and the planets in their orbits around the sun. And there wasn't any reason to think that this would work for other systems as well, that it was just, as it were, something that just kind of worked for the Earth's immediate environment. Newton himself believed that the universe was infinite in size, because he was a highly religious man. He had a very kind of strong view that God had a kind of infinite power, and therefore, why would he have created a limited universe? And so, very kind of strong view, very strong kind of faith in God of unlimited power and reach. But he'd also done some measurements, attempted to kind of measure the distances to some of the stars, found that they were immense, and so this idea of a kind of infinite universe also concorded with that, with those measurements. And for similar religious reasons, he believed in an eternal universe. So Newton's cosmological and theological views were mutually reassuring, mutually kind of reinforcing.
He observed that the kind of law of gravitational attraction, if you just kind of left that to its own devices, would actually pull the contents of the universe together in a horrible crunch. That's the nature of kind of gravitational attraction. Everything would eventually come together in this kind of crunch. And therefore what you needed was an omnipotent God to kind of hold the architecture of the universe in place. So interesting, as it were, overlap there between cosmological views and theological views. For almost the next 200 years, astronomical practice basically kind of sheltered under it kind of advanced under the shelter of the Newtonian cosmos. There were progressive improvements in the power of telescopes. You can see here the Herschel's 40-foot telescope built for the King, which these new telescopes revealed new vistas of stars, enough to occupy the labours of what is a very growing, rapidly expanding number of astronomers, both amateur and professional, through the 18th and 19th century. On the whole, astronomers seem to have taken the view that their principal role was just to kind of chart the coordinates and spatial relations of cosmic bodies as viewed from Earth, with a kind of underlying faith in the kind of basic stability of the cosmos enforced by gravitation. So their view is basically, there's enough of this stuff coming into view that our job is to identify where everything is and kind of locate its position. But there were some significant astronomical enigmas. For example, the status of these unmoving systems of clouds, nebulae. You can see a kind of drawing of the nebulae by William Herschel, which could be seen lying both within the Milky Way, but also outside the plane of the Milky Way as well. And that's a kind of a key issue, which I'll go on to talk about in a moment. Now, according to one hypothesis, which was quite widely advanced in the late 18th century and through much of the 19th century, all stars, even the Sun, had passed through a kind of nebulous stage, basically originating as a kind of cloud of incandescent gas that then kind of cooled, flattened into a kind of rotating disk, spinning off successive rings which then condensed into planets. And that's actually a theory that predicts modern day accounts of the origins of the solar system. Most importantly, however, it also moves away to some extent from this very kind of static view of the cosmos. It provides a kind of an evolutionary, dynamic view of the cosmos that actually predates Darwinian evolution based on biology. But it also seemed possible, as some of these nebulae were not confined to the galactic plane, that some of them were larger systems of stars that could not be clearly seen, because basically their location lay beyond the Milky Way. That is, they raised the possibility of the Milky Way, our own galaxy, is not the only galaxy that existed. It wasn't the Milky Way was not all that there was in the universe. In the 1750s, the philosopher Immanuel Kant famously claimed the nebulae to be separate island universes. But the issue wasn't really resolved until the 1920s as a consequence of two developments. The first development involved the creation of a reliable method of estimating the distance to stars of a certain kind. And those stars were known as Cepheid variables. The mathematics get quite complicated, so I'm going to sort of skirt and embarrass Masha over them a little bit. But basically, through this method, you could use this to calculate the distances to other stars, as long as they were in clusters that contained a Cepheid variable. And by such means, by focusing upon clusters of stars within the Milky Way, the astronomer Harlow Shapley, who was based at the Mount Wilson Observatory in Pasadena, California, determined a new estimate of the size of the Milky Way, and he found it to be immense, much larger than had previously been thought. He believed that this kind of huge dimensions of the Milky Way, so this is towards the end of the kind of 19 teens, so 1918, 1990. He believed this huge dimensions explained why the nebulae were so faint and couldn't be kind of resolved. It was not because they lay outside the galaxy, it's because, as it were, the galaxy that contained them was so large. And Shapley also calculated that our Sun was not in the heart of the Milky Way, that it's actually a rather kind of provincial little star, one of the arms of the Milky Way, which confirmed, as it were, the end of the view that we're at the centre, at least the Sun is at the centre of everything. So that's the first development, this ability to kind of calculate the distance to some of the stars. The second development involved a major advance in astronomical instrumentation, also at Mount Wilson. An advance which, in my view, is very, very much dependent upon broader processes of social modernisation in the United States. The observatory had been founded in the first years of the 20th century. Its location was chosen in part because of its relative isolation. At that time, there was limited light pollution from the surrounding settlements. This changed very rapidly because it's quite close to Los Angeles. And, basically, by the sort of 1940s, 1950s, it's a real problem for astronomers at Mount Wilson that they're getting that much light pollution. But one of the interesting things, of course, is the quality of the light in California was exactly what encouraged Hollywood studios to move their operations there, because Hollywood's not really that far away from Mount Wilson. So there's limited light pollution at this point. It's also high up on the mountain, above the cloud layer, so conditions for observing both the sun, it starts off as a solar observatory, and the night sky were really superb. Pretty isolated. In the early days of the observatory, basically the astronomers used to kind of team up for rattlesnake hunts in order to avoid nasty surprises during the times that they're kind of concentrating on the night sky. When I visited Mount Wilson a couple of years ago, I was just sort of walking in the woods nearby, and there's a snake crossing my path. It's still got that little kind of tinge of the exotic, at least for Britain. But the observatory didn't remain isolated for very long. Southern California, as you might know, was at that time the most rapidly modernising region in the whole of the United States. Los Angeles, which is visible from the mountain, was becoming a major American city. George Ellery Hale, who was the founder of the observatory, also established nearby the California Institute of Technology, which now consistently ranks as the world's best university after Southampton. And the successful operation of the observatory was increasingly dependent upon those sort of changes, those processes of modernisation taking root. By 1917, the Mount Wilson Observatory possessed the two largest telescopes in the world, one with a 60-inch mirror and this one here with a 100-inch mirror. But as you can imagine, these are kind of huge pieces of machinery, and they really couldn't have been built or funded without a kind of, as it were, an infrastructure of sort of finance and expertise around them. They were built actually in some major industrial centres, so therefore you need to kind of railroad, kind of bring them close to the mountain. You need expertise to sort of make them work. You need supplies of power, other utilities going up the mountain. A prosperous Los Angeles businessman paid for the mirror, for the 100-inch telescope, and more generally, the kind of observatory's work was funded by the Carnegie Institution of Washington, which is one of the new breed kind of philanthropic foundations with endowments basically generated from the profits of late 19th century industrial conglomerates. And so all of this is kind of possible as a result of this much kind of broader social context. But anyway, within a few years of Shapley's new calculation of the size of the Milky Way, the astronomer Edwin Hubble, you see here looking through the 100-inch telescope, identified a second variable those particular stars again, in the Andromeda Nebula. And that meant that he could use it as the basis for a distance measurement, to actually measure the distance of this nebula. And he found that Andromeda lay well beyond the vast dimensions of even Shackel's vast galaxy. The nebulae were separate galaxies, which meant that the universe was exponentially larger than previously been assumed. 6 years later, Nat Wilson became the site of another major cosmological discovery. For some time after Albert Einstein had completed his general theory of relativity in 1915, astronomers have basically been kind of reluctant to explore its implications for their subject. In part, they often freely admitted, because they found it difficult to understand. Astronomers had helped, of course, to prove the theory's validity. They confirmed the gravitational bending of light during the 1919 solar eclipse, which was a kind of key test of Einstein's theory. But its relevance for the sort of problems that they were interested in was not immediately evident. Basically, for studies of the solar system or the immediate stellar neighbourhood, you could use Newton's gravitational model just as happily as you could Einstein's. But the broader cosmological implications of Einstein's theory did attract considerable interest from physicists and mathematicians. Just like Newton had, Einstein favoured a static universe, a sort of eternal, stable universe. But he also recognised, just as Newton did, that his own theory would involve that universe's gravitational collapse. And so, Newton had brought in an interventionist God to kind of hold everything in place. What Einstein did was introduce into his equations what he called a cosmological constant, which is basically this kind of figure that stood for whatever repulsive force stopped the cosmos from crunching together. Other theorists, however, pointed out that what resulted most logically from Einstein's equations was not a static universe, not even one that was doomed to collapse, but actually a cosmos that possessed an outward, expansive force. According to the Belgian physicist, also intriguingly the Jesuit priest, Georges Lemaitre, this force might have had its origin in the explosion of what he called a primeval atom. Now that thought seemed counterintuitive to many, and to some extent it still seems counterintuitive to many today. How could everything in the universe be contained in a single tiny point? But the proposal was consistent with Einstein's most famous equation, E equals mc squared, which permitted enormous amounts of energy and matter to be compressed into the smallest units of mass. It was also a proposition influenced by the developing theory of quantum mechanics, which was really kind of growing in the 1920s, which was investigating that kind of theory, investigating the vast energies that were released by radioactive decay, and investigating the tendency of atomic nuclei to decay at random, without a determinable cause. And perhaps it was that, for Lemaitre, that prompted the primeval atom, as it were, to decay and explode. So Lemaitre, as a Jesuit priest, didn't even need his own Catholic God to initiate the creation of the universe. Now, at this time, Lemaitre was presenting a kind of speculative physical explanation for a cosmological model that he extrapolated from Einstein's maths. But in 1929, his theory received critical empirical affirmation in the form of new data from Hubble and Mount Wilson. Hubble and his assistant Milton Humason had recently added a spectrograph to the 100-inch telescope, and the spectrograph allowed them to identify whether the galaxies that they were looking at were moving, and in what direction, with what speed. Basically, the spectrograph recorded what you consider as the kind of light equivalent of the changing sound wavelength of a train as it comes close to you, passes by, and moves away. We all know that there's a kind of change in the fact when trains used to whistle, there was a change in the kind of whistle that the trains move by. And the spectrograph does the same thing for light. And what they discovered was that almost uniformly, the galaxies were moving away from each other. And moreover, that the most distant galaxies were moving apart most quickly. The universe appeared to be expanding. And if that was indeed the case, then the history of that expansion, if you like, rewound on tape, to borrow a metaphor from Hollywood Studios only a few miles away, the history of that expansion rewound could be presumed to have begun back in a single point in space-time, the Lemaitrie's primeval atom. And in 1931, on a visit to Pasadena, which was widely reported in the American press, Einstein finally conceded the argument the universe was in motion. And he declared his use of the cosmological constant to have been the biggest blunder of his life. Now, Einstein may have surrendered, but not everyone was convinced. There are a lot of us physicists who disliked the notion that the universe had its origins in a state, this kind of point of infinite mass that preceded the establishment of its own physical laws, and which they, as it were, couldn't see anywhere else in the universe, which didn't have a kind of any equivalence anywhere else in the cosmos. So it seemed to be a kind of hypothesis that it was not possible to prove correct. And there was also a lot that Lemaitre's model didn't explain, such as the formation of the elements, the development of the broader stellar and galactic architecture of the universe. Also, there was an age discrepancy. Hubble's own calculations of galactic distance and velocity, again, you kind of run backwards in time, resulted in a universe that was younger than the age of the Earth, as indicated by geologic data. So Hubble time, as it were, was counted at about 1.8 billion years at this point, whereas the age of the Earth was thought to be around 3 billion years. So how could you have a universe that was younger than the things in it? And Hubble himself was cautious about interpreting his data as conclusive proof of an expanding universe. By the late 1940s, however, one of the principal gaps in Lemaitre's model of the creation of the universe had been filled in, and that's the issue of the formation of the elements. And also a key physical test that might demonstrate the validity of Lemaitre's theory had also been identified. And here the scene switches from Southern California to the greater Washington, D.C. area. Until the 1930s, basically Washington, D.C. hadn't been a notable centre of scientific production, but the Carnegie Institution of Washington, the same foundation that had funded Mount Wilson, was kind of keen to develop a presence, a local presence, in the rapidly advancing field of nuclear physics. And therefore, it arranged for the appointment of George Gamow, who you can see in the centre here. I'll explain this picture in a moment, and Edward Teller, who's become the father of the hydrogen bomb. They both recently migrated, Gamow from Russia, Teller from Hungary. So they were appointed, the Carnegie Institution of Washington arranged their appointment to the physics department of the George Washington University. And the Carnegie Institution also funded an annual series of conferences in theoretical physics, which drew to Washington experts from around the United States and also from Europe, really indicating that the kind of locus of intellectual innovation in the field of nuclear physics was moving from, as it were, Europe, war-haunted continent, to the United States. What Gamow did was he began to apply his knowledge in the late 1930s. He began to apply his knowledge of nuclear processes to explore cosmic phenomena, beginning with the sun and the production of energy. But by the mid-1940s, just shortly before he was brought into the project that Teller was beginning to lead on the development of the hydrogen bomb, Gamow was proposing that fusion processes in the hot, dense conditions of an early universe were the source of the chemical elements, provided this was a kind of alternative to the more common suggestion at the time that the elements had been kind of cooked in stellar materials. The theory was explored in more detail by his doctoral student Ralph Alpha, that you can see there on the right, who used recently declassified data about fusion reactions produced by the Manhattan Project. And Alpha found that the sort of nuclear chain reactions that would have occurred in an early universe would have produced the elements of hydrogen and helium in exactly the proportions that are still observable in the modern day universe. And as hydrogen and helium are account for about 99% of all the atoms in the universe. That meant quite a lot as a sort of circumstantial proof. Alpha continued to refine and develop this theory in collaboration with Robert Herman, who he met whilst working at nearby Johns Hopkins Applied Physics Laboratory, an institution that had also been sort of set up relatively recently to invent advanced weapons. And they produced a very kind of extensive account of the process of element creation through to the eventual cooling of the early universe, which included, in this account included a critical and largely overlooked prediction. It predicted that the end of the fusion process would have released photons of light to basically kind of travel through the universe, which, as the universe continued to expand, would have stretched to microwave wavelength and cooled to a temperature they estimated of around 5 degrees with the lapse of zero. Here was something perhaps you could look for. Just to explain this, this is a bottle of Cointreau. Gamoth likes to drink. You see him sort of rising out of this, but they've replaced the Cointreau label with Yilem, which Helen will be able to tell you is a sort of, I think, a Hebrew word for original matter or primeval matter. The difficulty for Alpha and Herman was that in the early 1950s there seemed to be no astronomical instruments basically available that had the sensitivity to locate and to isolate and measure such a low temperature phenomenon as this kind of radiation. Moreover, although their work showed that the Big Bang theory provided an explanation for the creation of hydrogen and helium, it was not necessarily the only possible explanation, and they hadn't found a way to incorporate the creation of other elements, heavier elements, into their theory. And at least at this point in the early 1950s, that kind of age discrepancy problem remained. Although from through the 1950s, the situation kind of improved for them. Those measurements of the size of the universe started to be revised upwards, which actually meant that by the end of the decade, the lifespan of the universe actually comfortably contained better the Earth and stars. So in the mid to late 1950s, there seemed to exist no clear way of resolving the kind of stalemate between those who argued that the universe had its origins in a Big Bang and those who believed that it was essentially eternal, existing in a steady state. And the standoff between these two cosmological theories seemed kind of unedifying and intractable and kind of embarrassing for many astrophysicists. In this period, before the physicist Stephen Weinberg, the study of the early universe was widely regarded as not the sort of thing to which a respectable scientist would devote his time. One of the few places in the United States where cosmology was taken seriously was Princeton University. It was there, supported by quite ample grants from the US military and the National Science Foundation, that the physicist Robert Dicke had developed an interest in testing Einstein's cosmological models, but he also had the kind of freedom to do other stuff that he wanted to do as well. And in 1964, he conceived of a way to test his own preferred theory of the origins of the universe. His own preferred theory was that the universe had been formed out of the bounce from the previous version of itself. Dicke speculated that the bounce would have had to have occurred in conditions of extreme heat in order to decompose the old universe and allow the formation of the new. And some of that heat, Dicke suggested, would have survived into the present day in the form of microwave radiation. And he persuaded 3 of his postdoctoral assistants to explore the theory. One of them was going to try and calculate the remaining, the likely temperature of this kind of radiation. The other 2 were going to build equipment with the aim of detecting it. So the Princeton physicists were essentially looking for the same radiation that Alpha and Herman had predicted the existence of a decade or so before. God invented space, the astronomer Royal Martin Rees has observed, so that not everything had to happen in Princeton. At the Bell Labs Radio Research Laboratory at Crawford Hill, New Jersey, only 30 miles away, there already existed an antenna which was well suited to the observation that Dicke and his associates wanted to make. 50 feet in length, you can see it here, it's in the background there. 50 feet in length with a 20 foot by 20 foot aperture and a horn shape in order to kind of shield its beam from noise sources on the ground. The antenna had been constructed with the purpose of receiving extremely faint signals from extremely faint radio signals, which were bounced off the Echo satellite, which is one of the first experiments in satellite communications in the world. Bell Labs was the research arm of AT&T, which was the biggest corporation in the world at this point, very interested in preserving its monopoly in telephone communication into transoceanic communication, and satellites seemed a very good communication satellites seemed a very good way of doing that. So the Crawford Hill horn antenna was also used in 1962 to receive telephone and television signals from the Telstar satellite. Now, during the course of calibrating this antenna for both Echo and Telstar, Bell Labs engineers had found that they couldn't account for all the temperature that was measured by their system. What they did was, okay, we can't find the source of this, but let's just borrow it from the time margins of error of each component. They were often more interested in communication, not cosmos. But in the late 1963, the horn antenna passed into the hands of these two radio astronomers, Arnold Penzias here and Robert Wilson, who began adapting it for observational use, planning to enhance its already kind of striking sensitivity in order to make measurements of low-temperature cosmic phenomena. Now, they didn't know about the background radiation. They really had certainly Penzias had no background in cosmology. They were completely unaware of Alpha and Herman's work predicting the existence of a microwave background. And so they're basically very perplexed when they tested their antenna, which they thought they could refine perfectly, pointing it at an empty portion of the sky, and found that it registered a temperature of about 7 degrees Kelvin, which was about 4 degrees hotter than the combined total of all the sources of heat that they knew about from the atmosphere and from the antenna. And they spent much of the rest of the year re-examining their equipment, sweeping the sky, trying to work out where the source of this success came from. But whatever they did, wherever they looked, this kind of stubborn margin of about 3.5 degrees Kelvin continued to crackle through their antenna. And it was only in February 1965 that Penzias and Wilson learned about the work that was being conducted by Dickey's group at Princeton. Penzias phoned Dickey to find out more, and when the call came through, Dickey was actually in his office with his 3 associates, and they were discussing the kind of progress that they were making towards construction of their own antenna. Penzias and Dickey discussed the excess temperature that had been detected on Crawford Hill, and when the call was over, Dickey turned back to his group and said, "Gentlemen, we've been scooped." Shortly afterwards, Dickey's team went to Princeton to inspect the Crawford Hill antenna. It's clear to them that Penzias and Wilson had been really careful in their work, that their measurements could be caused by a system fault or by any other local source. Dickey then explained to Penzias and Wilson his ideas about how the heat of the early universe would have left behind this kind of fossil record in the form and the range of the radiation that they detected. Penzias and Wilson were pleased to have an answer to the puzzle, and it was agreed that the two groups would submit companion articles to the Astrophysical Journal, reporting first the Princeton theory, and secondly the readings from Crawford Hill. And I mentioned this when I started the day. And it was from the Astrophysical Journal, as I said, that the news of the discovery leaked out to the New York Times. Now, in and of itself, front page splash in the New York Times was not enough to transform scientific cosmology. The existence of the cosmic microwave background radiation had to be confirmed by other measurements as well, and Penzias and Wilson began to make other measurements, and so did the Princeton team when their antenna came online in September 1965. By 1967, as a result of these measurements, confidence in the Big Bang theory was growing, and as a result, the field of scientific cosmology really...
Well, thank you very much for taking that marvellous journey of the sort of history of cosmology there. I'm sure there's lots of questions. To start, anyone want to start us off?
I think I'm saying that the term Big Bang started off as a rather insulting expression by Treadwell, I think, wasn't it, who said that, "I suppose you think the universe started in some kind of bang."
Yeah.
I would say that to Treadwell, I think, it's about steady-state continuous creation. I think you've never explained how that happened.
Yes, no, you're absolutely right. So it begins as a derogatory term, and one of the reasons that Hoyle hated the idea of Big Bang theory is before it was religious at its core. It was essentially a
Christian doctrine. He was a kind of avowed atheist. It wasn't helped by the fact that the kind of Pope came out shortly afterwards and endorsed it as a model that was consistent with Catholic theology. There is in the 1950s and the early 1960s quite a debate that goes on between largely British state status. This is an idea generated by people who are really organised around kind of Cambridge, people like Oljver, like Thomas Gold and Herman Longley, and people like Prof, Oljver, and Herman. What's interesting, however, is that there doesn't seem to be a way to resolve it, and so that makes a lot of other people who might be interested in cosmology sort of give up and well, we're never going to solve this. And so it's only in the kind of big 1960s that you get a resolution of this issue.
Did Hoyle go to his grave living in steady state?
Yeah, pretty much. I mean, I don't have a lot of sort of research in this. All of the steady staters have a crisis of confidence in their model in the mid 1960s as a result of this, and so they start to kind of concede some of the ground at that point. And then by the late 1960s, they go, oh well, actually we quite like this steady state model, and they try and find ingenious ways of questioning the data. Maybe the radiation comes from a discrete source as opposed to being a kind of background radiation. A discrete source that we just don't understand yet. That sort of view. And they continue to hold to it to the point that by the late 1980s and early 1990s, they're starting to argue amongst themselves in quite vigorous terms about who first came up with this, what is now regarded as a wrong theory. So that they all want to kind of claim the idea that theirs is the original kind of idea. Gold, or actually, I'm the one myself in shape this.
Presumably, ridiculously oversimplistic. The Catholic Church that you mentioned, they're saying being ridiculously oversimplistic, but yes, the Big Bang happened, but God pressed the button. Is that?
Yes, I mean essentially that, because one of the problems with the Big Bang is that what actually causes the bang is, as it were, beyond physical laws. It's difficult to explain. Now, people like Stephen Hawking have done quite a lot of sort of work on this and have sought to explain it, but their explanations are quite complicated and perhaps too opaque for too difficult for many ordinary people to understand. And so that kind of that question does very much remain. That you can see the bang itself. What follows from the bang is essentially sort of secular process. But if you want some kind of comfort, religious comfort from this, then the question is what makes it actually happen. But as I said, the kind of view these days is that some form of kind of quantum fluctuation.
To what extent did your whole history, is it driven by people getting deeper insights? And to what extent is it driven by advances in technology?
Yeah, that's a really good question, and I think the answer to it is that it's a real mix. I mean, my particular interest, what I'm kind of writing about in my book, is that although these days we very much consider cosmology as being big science, it's the Large Hadron Collider, it's the Hubble Space Telescope. These are kind of massive infrastructure projects. The kind of the formative years of cosmology in the 20th century tended to be discussed in quite kind of biographical terms, or told in terms of the kind of biography of the theory itself, how it sort of developed over time, and how various people kind of contributed to it. My argument is that a lot of these key innovations take place and coincide with and are dependent upon broader social and cultural factors. So, you can't tell the story of the Mount Wilson Observatory and the availability of the 1,000-inch telescope unless you start putting that in a much broader picture of modernization in Southern California. You can't tell the story about why Prof is in Washington, D.C., his association with Alpha Herman, the fact that they were all at various points employed by the Johns Hopkins Applied Physics Laboratory, Prof as a consultant, and exchanging ideas in that arena.
you know, without telling a story about modernized, as it were, the development of Washington DC as a sort of site of scientific production. And you certainly can't tell the story of this without talking about satellite communication, about AT&T, the biggest, you know, company in the world. You know, so there are these, I think, a much larger sort of story that you can knit this into.
Yeah. Okay. Yeah. I mean, were you saying the fact? I think you mentioned about it was like the Big Bang. There was a coming together, a compression before, and then the Big Bang was the second part of the process.
Well, this is the theory that Robert Dickey very much favoured, largely on philosophical grounds. And I mean, some of I've gone through his papers, and he notes at various points that it's kind of Hindu-esque, Hinduist conception of a kind of cyclical universe, the one that expands and then compresses, and then expands and then compresses again. And that's an interesting sort of sub-theme of certain kind of ideas about cosmology that you do see throughout this period. The problem is, of course, identifying how do you prove that, because in the moment of compression, new laws may be created, and so it's sort of difficult to prove. And also, Dickey itself admitted later that he's coming up with this theory in 1964, and fairly shortly afterwards, Stephen Hawking comes up with his sort of explanation of the sort of singularity that would have occurred at the kind of original moment in the universe, and how impossible it was as a result of that singularity to know anything about what occurred before. And so Dickey sort of said, maybe I wouldn't have thought about that if Hawking had done his work 2 years earlier.
I'm getting a sense from the way you describe the development of science is that you need to build that infrastructure in society to kind of, if you like, at the top of that is an instrument, and associated with that is someone with ideas, and the two come together and you get groundbreaking ideas or space-breaking ideas, whatever you want to say. And as things have gone on, so they become more complex. Would you say now that you've got a situation like the Large Hadron Collider, you've always got to have that enormous infrastructure around the experiment rather than just the society and the industry and the finance and all the rest of it, and that we're probably not going to have a future whereby Fred Broggs comes up with the idea because it's now the team with this big machine and everybody lays claim to something. Is that how you see things going? Or?
Well, of course, the Higgs boson, the idea of the Higgs boson is generated by somebody kind of more or less working, as it were, the individual independent genius, of course, but then what it requires is this huge infrastructure actually to find the sort of particles that now seem very important for fleshing out this kind of Big Bang model, and indeed for testing inflation theory, which we'll be discussing later in the day, basically require a lot of complex instrumentation. They require a lot of people with lots of different skills. They need a lot of money, and so it is a much more kind of corporate enterprise. Whereas, the sort of stuff that I've been talking about, does depend, as I said, on a lot of capital and so on. But it also, there is scope for the kind of serendipitous discovery and the kind of individual thinker sort of coming up with a theory that then needs to be tested and so on. So I think generally I would agree that the pattern that you've just tracked is right. Of course, it doesn't mean that there aren't exceptions.
The more money you spend, the more the prestige of nationalism, which happens in that, or why these charities want to fund that. Apart from what you might use it for, there's a prestige of modernism in being the leading country, and there's still a will in this country to contribute to that, and that's where the money comes from. If we didn't believe that culturally it was important, not instrumentally important, we wouldn't spend that money on hadron colliders because we don't know that we're going to get anything back, do we?
Well,
so it's still political in that sense.
It is, but it's also, I mean, the Mount Wilson Observatory is funded by, a philanthropic organisation. What's happening in the Carnegie Institution and the John. One of the problems for like Alpha and Herman is that there isn't a huge amount of tolerance for their work on cosmology for the Applied Physics Laboratory. It's about making weapons, so they eventually leave and go to other places, which stops their work. Because they're told that in these other places, General Electric or General Motors, there will be they'll be sort of sympathetic to their work in cosmology. But of course, they get there and they find that that's not really the case. They want business-focused work. And similarly, kind of Kendrick and Wilson have difficulty sometimes in the 1960s and early 1970s persuading people to allow them to continue doing what they're doing. They have to kind of work on satellites and lasers and other material. So there is a kind of stakeholder interest in this, and is the idea of fundamental advances enough to make people, as it were, write an open checkbook? I don't think that's the case. For example, yes, I mean, CERN is a sort of wonderful example, but it is a kind of cross-national enterprise. When the Americans wanted to develop a big super collider in the 1980s and 1990s, you get kind of senators saying, well, okay, we might find some interesting stuff about the origin of the universe, but do you really want to pay for it? It does seem, it can seem to those sort of constituencies a rather kind of abstract, remote thing to want to find out about when you've got a lot of other more compelling issues that are going to kind of drive votes.
Okay, well, thank you very much everyone for asking questions, and to Kendrick for talking us through all of that. And we'll be around during the rest of the day if you want to